All right, physics reacting video number 74, I believe. Did a search this time for literally this phrase, optics review, and found something here. So here we go.
So I'm recording starting now. So waves and optics. This equation is the wave equation. So it is actually one that spans both of these units, the optics unit and the duality unit, because obviously wave particle duality, this is relevant as well.
Cool.
In this equation,
That's super cool.
We've got three variables. Hopefully you know what all those mean by this point. I'm not going to go through all the units, etc. You can come back to this slideshow, which is being recorded, if you look at those things. But the key things that I want you to get out of this are, what are the relationships that are relevant here? Because you mostly use this equation sort of conceptually. So there is a linear relationship between lambda and v, which means that for a given wave, if its velocity increases, the wavelength is going to increase as well. I kind of use this car model. You picture these cars driving along, and the cars are the crests of the wave or something. And if those cars are driving along at a slow speed, they're close together. And as soon as they hit a zone that's got a higher speed limit, right, they end up spacing themselves out more to accommodate the higher speed limit. And so that's kind of how I concept.
So I really like that car analogy. It's interesting, when I was a kid, I didn't understand, and so many of my friends would say the same thing. You're at a stoplight and you're smashed against the car that's right in front of you. And the light would turn green, and everyone would be like, well, why does it take so long to get everyone going? And, because if we all were to start at the exact same time and go that speed, that would be incredibly dangerous, right? We need that 2-second gap minimum between cars. And so it actually times out really well. If you happen to know how many cars are in front of you at a stoplight, multiply that number by 2. And when the light turns green, count that many seconds. I'll bet you anything that's when you start going, because you need that gap. And so in the frame here. So I really like this idea, and it ties so well with this sentence down here, right? That the wave depends only on the medium, the F depends only on the wave source, and then lambda is dependent on both. I just love that, right? Because how many cars are there is basically frequency. What's the speed limit is V, and how they're spacing is dependent on both of those. I really, really like that. And so to write it this way, that medium up here, source down here, these are sort of controllables, and then this is just how the system reacts. I think that's actually really cool.
Or understand that linear relationship. But the key thing, and this is down here in the notes, is the velocity of the wave depends only on the medium. So that spacing based on velocity is only going to change if the wave is moving from one medium to another through a wave boundary. So through a medium boundary. So the velocity of a typical wave does not change as it moves through space, and it doesn't depend on the frequency or the amplitude or anything else. It only depends on the thing that we're moving in. And when we shift mediums abruptly, the wavelength is going to be changing as well in a linear fashion. So higher velocity, higher wavelength. The second relationship has to do with lambda and frequency, and this one is a lot more intuitive to people. The idea being, if you have a really high frequency wave, if the wave source is jiggling really fast, the wavelength is small. The waves are close to each other. And when the wave source is jiggling slower, then we have the waves further apart from each other. So that...
it's interesting to listen to her vocabulary, right? And to realize, to get it exactly right, which she's done a couple of times, is just sort of ponderous, right? It takes forever. So she said the waves are close to each other. Earlier she said the wave crests are close to each other, right? I don't think this is confusing. I think that the students understand what's being said. What's hard about all of these wave things is that it's like one gigantic thing, right? So to break it up into its small parts, maybe a crest, maybe a particular section of it is hard. And I think that she's doing a really, really great job here. It's interesting. So she's mixing and matching her types of waves, right? So she talks about light here, she talks about sound here, she's got this down here, so she's talking about particle waves as well. So I think that it's really, really interesting to say, look, all of these things are the same. And for me, right, the matter wave stuff, it's so interesting, right? Because every weird thing that you learned about waves tends to apply in the quantum realm where you have matter waves. And so, for example, the Heisenberg uncertainty principle is just the wave uncertainty principle applied to matter waves, right? And I find that really driving home everything you know about waves suddenly comes into play when it gets to matter waves, and it just leads to things that just don't make sense, and yet it happens all the time. Tunneling happens all the time with optics. The uncertainty principle happens, I mean, all the time. I mean, it's just how recorded music works. It's how MP3s work. And so I think that it's so interesting to see all of these connections. I think she's doing a great job.
That's an inverse relationship, and that one should be more intuitive. There is no relationship between velocity and frequency because those are the independent variables. The only way you can control the velocity is by changing the medium, and the frequency only depends on the wave source. Lambda is the thing that links them and is dependent on both of those variables. Any questions on this equation?
I was just thinking about this, like when does this break down? Because, most things like this, most things like a big fat no, break down at some point. And dispersion, right? So light, different colors travel different speeds in materials. So the frequency of the light determines the speed in dispersive materials. Luckily, like air is not dispersive for sound waves. Could you imagine if air was dispersive for sound waves? I mean, could you just imagine if Mariah Carey's voice traveled faster than, I don't know, some low person's voice? It would be so weird. Things would be out of sync. And so luckily air is pretty non-dispersive for the frequencies that humans can hear. So that's pretty cool.
Hopefully we'll type them into the chat or turn on your mic, which would be faster than typing things into the chat if you can.
Oh, this is live.
Typically this is used for regular waves, but there are occasions when you have a de Broglie wavelength problem. If you watch the duality videos, and you are asked to find the frequency of the de Broglie wave or something, and you would be using this equation with the v being the speed of light in that case. In the chat, how many of you have watched the duality videos, just out of curiosity? I know you're not all taking the test yet, so not all of you will have watched it, but can you just give me a yes or a no?
Oh, she just said something really interesting. So first of all, to ask like, hey, no judgment here. I just need to know my audience. And then she said, not all of you have taken the test yet. So it sounds like this might be a little bit go at your own pace, or maybe like a standard space grading type situation where students can sort of redo stuff. And so it's really interesting to sort of get a sense of what your audience is when trying to figure out exactly, how to help them the best. It's also interesting the way that she recorded this because we don't see the other people, and I'm wondering if we're even going to see the chat. So this is very carefully framed to protect the students. This is on YouTube, obviously. I found it on YouTube, so it's public. But it kind of looks like she's done a really great job of protecting the students because, sometimes you have to really worry about that. I sometimes ask my students if they care, and they'll say, well, I don't care, but I realize that the students who do care aren't going to speak up. And so, I'm really careful about that. But, it took me, 3 minutes into the video before I even realized that this was live. So let's see what happens. She just asked for some stuff in chat. I wonder if we're even going to see it.
Out of curiosity, have you watched those videos yet? Okay, so let's move on. All right. This is the second wave equation that would be relevant. And this one, I would call this the index of refraction equation. It basically tells you this idea that the speed of the wave depends only on the medium. And to that end, all media have a characteristic index of refraction, which is this n value, and it's a material constant.
So it's interesting. I've talked a lot about cameras that have autofocus and how that can be a problem. It's almost like her audio has a similar problem. Have you noticed, right? Sometimes it's in, sometimes it's out. I wonder if there's like an auto gain feature in the camera and the microphone. I mean, it's not a problem. I can totally understand her, but I've noticed it, and I just think about how these small little things that we continue to work on. But knock on wood, we're coming out of the pandemic, so I wonder if the progress on that technology will slow down a little bit.
So this is not something that changes. Glass always has an N of roughly 1.5. Water is always 1.3. Plain air is basically about 1. Diamond is always 2.4. So each material has a set constant value. And we can use that constant value to basically scale the speed of light through that material based on the maximum speed of light, which is the speed of light in a vacuum, or c. So this equation is a pretty straightforward one. You're always going to...
So I'm just going to pause for a second and talk about how it sounds like she has some de Broglie wavelength stuff, some matter wave stuff in here, which means this class might also have a little bit of relativity in it. I don't know. Relativity is really tough because so much of what you build there is that light travels at the speed of light, period, right? Like if there's this cosmic speed limit, and it leads to all of these super strange things, time dilation and length contraction and all that kind of stuff. And so it's been fascinating as I've taught different classes, different mixtures of topics. You occasionally get the students who say, hang on a second, you said that the speed of light is the speed of light, and suddenly you're saying that light decides to slow down in media. How does that affect relativity? And so it's really, really fascinating to talk about group velocities versus phase velocities. How fast do photons fly, right? So photons really only can fly in a vacuum, right? Otherwise, they smash into things and they excite something, they dump their energy in, and then those things then re-radiate. But photons travel at the speed of light, don't they? And you can see there's problems with that particle model, there's problems with the wave model. It gets really, really hard. And I think that it's interesting that in a class, when I've taught that this is the only time we're really going to hit the speed of light, super easy to show, hey, look, light bends, hey, you can do some experiments with, troughs of water and say, wow, this really did take a little bit longer to reach the detector. It's actually pretty easy to prove, and yet when we get around to relativity, we say, oh, the speed of light is the speed of light, period. Everybody sees it the same way, period. It doesn't matter, and all of a sudden you're like, what? So being inside a material seems to affect it. And remember that most materials, most everything is empty space, right? So it's just wide open spaces between the protons, the neutrons, and the electrons, which are really just these wavy things. So I think that it's really difficult to hold all that together. So I don't know if this happened in her class. I was just guessing because of the de Broglie stuff that maybe there was some relativity stuff in here too.
To plug in 3 times 10 to the 8 up there for C. You'll be usually given a value for N, although occasionally you'd be given a V and asked to find N or figure out what the medium is. And this allows you to calculate V. The one relationship that's relevant and useful to have in your brain is that N and V are inverse. So the bigger the N, the smaller the V, because it's essentially a ratio, right? It's a ratio of speed of light to that speed. So the bigger the ratio, the smaller the V value ends up being. So the larger N means slower light in that medium. And a note just at the bottom, N can never be less than 1 because that would mean that material will be faster than the speed of light in vacuum. And one of the fundamental tenets of physics is that's the fastest light can ever move. And so the typical range on like sort of typical naturally occurring elements is from 1, which is air. Air is just slightly more than 1. It's almost a vacuum, but not quite. But we assume it's the same as a vacuum. Up to 2.4, which is diamond. And so speed of light in diamond would be the slowest naturally occurring substance that it can move it.
So I'm just going to pause right there and talk about how she's now gone 5 minutes with just 2 equations, right? So there's so much in those 2 equations. She's unpacked it like crazy. It's so interesting how compact our equations are and how much information they talk about. So I think that's really, really interesting, obviously prepping people, what's called optics review. So I'm guessing this is prepping people for some sort of assessment. The other thing I was going to talk about really quickly was, she was talking about light has this ultimate speed limit, but then when it goes in materials, it goes slower. And again, back to relativity, we talk about how however fast light goes is the ultimate limit. Nobody can go that fast. And yet it's fascinating, right? So in materials, light can slow down, and occasionally you can have particles going faster than that speed. So you have particles that are moving faster than the speed that light is traveling in that medium, but definitely still going slower than the speed of light in a vacuum, because particles have to go slower than that. So that's Cherenkov radiation, and it's just this super cool thing that you see. You're like, whoa, what the heck is that? And you realize, oh, it's this extra light we see when something travels faster than the speed of light, which should blow your mind. But you say, oh, well, it's faster than the speed of light in the material. It's just like a shock wave in sound, for example. So super interesting. Love the fact that 5 minutes in, still just 2 equations and really hammering home all of the properties here.
Questions on this slide? Okay, I assume you guys are going to turn on your mic and ask a question so that we can.
I heard a really interesting description of what teachers do when they ask for questions. It's embarrassing because they were talking about me in my class. So does anyone have any questions? and I'm purposely blinking here, and they were saying how it's the Dora the Explorer moment. So in the old Dora the Explorer TV show for kids, Dora would ask her audience a question, and she and her little paddle boots would sit there and stare at the screen and kind of like go like this, and then blink their eyes every once in a while. And then they'd say, yes, great, and then move on. And so the student was saying that's what happens. You get the Dora the Explorer moment when the instructor asks a question.
Get through it quickly. All right. So these equations I'm going to go through fast because I'm going to come back to them at the end of the slideshow when we talk about concepts. But briefly, just so you have it all together, that equation, if you're looking at your equation sheet, is known as Snell's law. And we use this equation for calculating, whoops, what just happened there?
Whoa.
Come on. All right, sorry.
So I just want to talk about this in a second.
All right, so we use Snell's law.
Okay, so that took her maybe 10 seconds to fix. That was so fascinating. Things happen, right? Things happen in class. And the mistake I make is I start saying out loud my entire thought process to fix it because I'm trying to model for students how to think through problems. And that makes sense if I'm trying to solve a physics problem or a programming problem. But if you're just trying to solve a logistical problem that helps you get back to teaching, it might not be good to explain every step. Oh boy, okay, this is Zoom. I think what I need to do is hit the back button and then reload the presentation and then get it to be presenting again. She just did it. And a whole bunch of things were going through her brain. She just did it because she knew that within 10 seconds she could get it back to this screen, which I think is so cool. I mean, such professionalism, right? Like the ability to not panic, like, oh, what happened here? But because it wasn't something we necessarily need to model for our students, she's like, I can fix this. Bam, here you go. In fact, I wouldn't even be surprised at all if she could have just kept talking about Snell's law while she did it. That was pretty amazing. Now that I pause, though, I'll say that this is really, really interesting. I have a suspicion this has to do with just making sure that you understand how your calculator is set, because obviously you can use degrees or radians or gradients or whatever the heck you want for the angles. So I think this is just like, hey, don't forget, you have to know what your calculator's doing here. Just looking at what else is on here. Yeah, super cool stuff, man. There's just so much here. Obviously prepping to do some sort of assessment or something.
For calculating how much a light ray bends as it moves from one medium to another. So whenever you have two different media, we know that the speed of light is going to be different speeds in those media. If the light ray goes straight into the medium boundary, it's going to go straight through, but it's going to speed up or slow down. In this case, we're going to slow.
I just realized what this is. I was like, what is she drawing there? She's talking about small n, big N. It's literally a big N. And I love how she's showing, it's fast, slow. Man, it's just this visual alone is pretty cool.
Down as we get into a bigger value of N. But if that light ray hits the medium boundary at an angle, okay, then that light ray is actually going to bend. And that is known as refraction. So this equation essentially compares those two angles. This would be the incident medium, Ni, and this would be N1 and N2. This is the refractive medium, the second medium we go into.
All right, I'm just going to stop it right there. Lots of really, really great stuff. Again, 7.5 minutes in, and we're only at the third equation. And I think that really trying to drive home how students need to understand that their equation sheet, if they have one, I mean, this is only going to take up 3 tiny little spaces on their equation sheet, but to just say, look, you have to understand that just how many relationships are present in here, and just how it's like the entire story of how waves propagate is basically these 3 equations. I just think that's so cool how she unpacked it, because you could just imagine students saying, okay, I just have to have these 3 equations on my cheat sheet and I think I'll be able to do it. And as soon as I see the problem, I'm just going to hope that one of these equations has all of the variables that I want in it. But by driving home exactly what they're meant and how they are telling us really interesting stories about how waves propagate, I think students can feel a little bit more relaxed. Like, okay, light bends. Which one has the bend? Well, bend has to do with angles, must be this one. So I think that's really, really great. All right, everybody, have a great day. And remember, physics teachers are awesome.